Assalamualaikum and greeting to all. I am Muhammad Johari bin Jamaludin from the Mechanical Engineering Department from Politeknik Muadzam Shah. Today I would like to present my project about the parameter optimization of the friction stir welding process by using response surface methodology on DISSIMILIAR welded aluminum alloy 6061 and aluminum alloy 7075. What is the technology of the friction stir welding in the joining process? FFW solid state welding process is invented and patented by TWI in 1994. It is a non-consumable rotating welding tool in the plug into the adjoining parent material. Frictional heat generated by the tool shoulder during the process causes the material to the soften and local plastic deformation to occur. Positioning of the material, they have two sides. First is the advancing side, and the second we have a retreating side. What the advancing side? The advancing side where the rotating tool move in the same direction of the transverse direction, and then the retreating side where the two rotation in the opposite of the transverse direction. Based on the previous study, has revealed that material at the advancing side with a low strength properties show much more effective on the mechanical testing. And at the welded area FFW, in general, the microstructure FFW joint is divided into the four regions. First is the sterile zone. Second is a thermomechanically affected zone. Third is the heat affected zone and the base metal. And what the advantage we using the FFW for the joining process? First, they have energy efficiency, no need the filler. Second, environmental friendliness, no toxic fume use, and then non-consumable. The steel, we using the steel pin. And then for the FFW, we apply to the aircraft and the aerospace industry, shipbuilding, train body frame, and the automotive industry. Why we join the material aluminum alloy 6061 and aluminum alloy 7075? First, for the aluminum 6061, the application in the shipbuilding, aircraft structure, and automotive part. The contain major alloy aluminum of the aluminium, magnesium, and silicon. Weldability, good toughness, and surface finish. Prevent the atmosphere and galvanic corrosion. Also, moderate strength around the 370 megapascal. And then for the aluminium 7075, application in the aircraft and aerospace structure. Contain major alloy element is aluminium, zinc, and magnesium. Also, they have excellent corrosion resistance, higher strength around the 500 megapascal, and good formability and weldability. Why we combine this of two materials? Of course, first, lightweight and have a strong structure of the general transportation, with weight reduction in the automotive, aviation, or marine industry, increase the fuel efficiency. Particularly famous DISSIMILIAR joining is the between aluminium and steel. Since such a joining have a major application in the field such as automotive, aerospace, and marine industry. Joining of the two materials is required in the sum of this application, while DISSIMILIAR aluminum alloy cannot be welded by the conventional welding process. Also, has a high resistance to corrosion compared to the steel. We go to the process parameter. Okay. For the FFW, we have a rotation speed. We have several process parameters, such as a rotation speed, traverse speed, tool geometry, pin diameter, tail angle, shoulder diameter, and axial force. In this study, we just use the two parameters, rotation speed and traverse speed. The rotation speed and the traverse speed govern the amount of the friction heat generated and subsequent plastic deformation and deformation heat and influence the welded joint. Mostly all the available literature focus on the microstructure and mechanical properties under different process parameters such as the rotation speed and welding speed. Various statistical and mathematical methods including the regression, Taguchi, response-based methodology has been used by the researchers to model the process parameter in FSW. Okay. For problem statement, most of the experience did not state how the optimum parameter for the process were the empirically and theoretically obtained of the dissimilar aluminum alloy. On the other hand, the study on the joining dissimilar alloy and the impact toughness behavior of the weld joint are very few. There are also a few mathematically way to identify the optimum parameter for the friction stir welding. A modern numerical study on the FFW in the aluminum alloy only in the limited work in the DOE strategy, particularly response surface methodology. The study to investigate the parameter optimization of the dissimilar FFW between aluminum alloy 6061 and aluminum alloy 7075 using the RSM. In the study, the effect of the rotational speed and welding speed on the evolution of the impact toughness of the welded joint has been investigated. The suggested way to identify the optimum parameter of FW is by using the RSM. RSM as a systematic approach to identify the optimum design of the performance. Thus, it can be utilized to identify the optimum parameter during the fabrication process. The objective of this research to investigation the aluminum friction welding using the RSM method are listed as follows. First, to investigate the effect of the FFW parameter on the mechanical properties of the welded joint. Second, to investigate the optimum parameter for the FFW between aluminum alloy 6061 and aluminum alloy 7075. And lastly, to analyze the microstructure of the joint between two materials. The scope of the study, first, to fabrication of the aluminum alloy 6061 and aluminum alloy 7075 FFW with parameter optimum by using the milling machine. Second, investigate the specimen mechanical properties of the weld using the Chappie test and viscous hardness test. And then the third, analyze the microstructure chain of the weld in the aluminum alloy 6061 and aluminum alloy 7075 using an optical microscope. We go to the methodology. This is a process flow for the process FFW. We starting with the preliminary experiment, and then we do the design of experiment, and then we follow by the FFW experiment. After FFW experiment done, we go to the mechanical testing for the impact test, and then after that, all the data we put the ANOVA, and then we come up with the mechanical model, and then after that we validate the data and run the parameter optimization, and then after that we analyze the microstructure and the hardness test, and then we get the result and the process parameter we use. Okay, for the process parameter we just use the two parameter. For the variable two parameter, first is the rotational speed, second is the welding speed. For the rotational speed, we use the 900, 1000 and 1100 RPM. Also for the welding speed, we use the 90, 100 and 110 for the millimeter per minute. But we fit for the T angle 3 degree. This is a tool geometry we use. For the sample preparation, for the sample dimension, we follow as a specification of the ASTM E22-60B standard. Subsize specimen we prepare due to different thickness. This is our sample. Here is our run of the experiment. For statistical analysis, first, after we get the result, we put the result into the ANOVA table, and we can get the main effect plot and counter plot and the space plot. And then we compare with the actual result for develop the mechanical model. And then for optimization based on the highest impact toughness. And then we compare with the predator. This is our FFW setup before we run the experiment. The figure show the positioning during the experiment, and then we put the aluminum alloy 6061 to the advertising side, and then aluminum alloy 7075 to the returning side. Then we go to the result and discussion. Okay, for the figure show the weld experience of the FFW. Okay, based on the experiment number 1 until 5 and 7 show some the flash and the surface galling. The defect mostly at the returning side where the aluminum alloy 7075 was allocated. And then we can see experiment number 1, 3 and 4 show the more flash at the lowest and highest returning speed and the welding speed. Most of the experiment they have a flash, some are from the small pin area. And then after that the experiment number 6 and number 9 show very smooth weld appearance with the no defect. The defect will be degrading the mechanical properties. We go to the result for the impact test. Overall, the impact toughness FFW welded joint is the highest compared to base metal. The lowest impact toughness is a 3.401 at the 1000 and 100 RPM at the 110 mm per minute. The highest impact toughness is a 5.404 Joule at the 1000 RPM at the 110 mm per minute. The impact toughness for the base metal aluminum alloy 6061 highest compared to the aluminum alloy 7075. Even aluminum alloy 7075 is higher strength properties. Based on the impact test result, the rotational speed of the tool increased from the 900 RPM to 1000 RPM. The impact toughness of the joint also increased. Afterward, increase in the rotational speed to the 1100 RPM, the impact toughness is decreased. This significant in the total absorbed impact toughness can be related to the microstructure modification induced by the FFW process, such as refinement and the roundness of the reinforcement particle and reduction of the metric grain size as shown at the figure. All the sample fracture at the SW region due to V notch was allocated based on the observation, and all the sample had a brittle fracture. This is a result show the statistical analysis, the mechanical modeling. The value of the regression close to the 1, and the value P for the model linear and square, and the interaction show less than 0.05, and leg of a fit also less than the 0.01. All the process factor terms are very significant. The graph show the main effect for the toughness, the impact toughness. The maximum value for entire parameter will produce maximum value of the impact toughness. Rotational speed and welding speed give the significant effect on the impact toughness. And then the figure show the surface plot above show the effect of the rotational speed and welding speed on the impact toughness. The figure indicate the impact toughness increase with the increase the rotational speed from the 900 RPM to the 1000 RPM, and the welding speed from the 90 mm per minute to 110 mm per minute, but decrease at the rotational speed 1100 RPM. This is our mechanical model. So we can produce finally our mechanical model for the energy impact. Okay, this is our model validation. Okay, structure diagram between the actual and predicted impact the toughness value and residue tend to be close to the diagonal line. It is a proof that the model is the acceptable is the estimated response. Average the error value around the 1.915% only. And then this is a figure show the parameter optimization. The figure show the optimum frictions the welding parameter to achieve the maximum impact toughness. It is evident from the figure that the higher impact toughness is achieved at the return speed of the 1000 rpm and the welding speed of the 110 mm per minute. This is a validation experiment. Okay, the predicted result is around 5.37 joule. 5 samples were performed in the impact toughness. Comparing the actual and the predicted result, the calculated average error is a 1.15%. The small error value indicate the high accuracy of the predicted model. Okay, now we go for the microstructure analysis. For lowest impact toughness, steel zone show the fine grain size. Thermomechanical effective zone show the elongated grain compared to the steel zone. Heat effective zone show the uneven grain boundary. The substituent grain refinement in the aluminum alloy in fact was observed in a nugget of the both welded joint, as one can see by comparing the microstructure on the base material and nugget zone in the both sides. This effect due to the dynamic recrystallization induced by the several deformation and concurrent frictional heating during the FSW. We go to the microstructure analysis for the highest impact toughness. Steel zone show the fine and exquisite grain size due to fully recrystallization. Thermomechanical effective zone show the elongated grain compared to the steel zone. Heat effective zone show the closer and the elongated grain size compared to the steel zone and thermomechanical effective zone, but small heat effective zone grain size compared to base metal. The homogeneous distribution of the reinforcement particle is one of the main requirements to achieve a good mechanical properties and in the discontinually reinforcement composite. We go to the hardness analysis result. Okay, this is a hardness analysis result. Hardness analysis result in the heat effective zone low the hardness result, show the low hardness result. Thermal exposure causes the grain to grow. Grain become the causes as they are located further away from the steel zone. Steel zone is the higher hardness result because the metal plastically deform, reduce the disallocation of movement. The grain boundary thus become the main obstacle to the slip of the disallocation. Hardness decreasing with the increasing the grain size. What we can conclude? The impact test show that the total impact energy significantly increased in the FFW welded joint compared to the corresponding base material. The maximum impact toughness was observed at the 1000 rpm and 110 mm per minute. The most effective parameter on the impact toughness response are the welding speed and rotational speed respectively. The rotational speed has a most significant influence on the impact toughness. The optimum parameter for the FFW between aluminium alloy 6061 and aluminium alloy 7075 is when the rotational speed is the 950 rpm and welding speed is the 110 mm per minute. The impact toughness of the FFW by using the optimum parameter is the 5.43 joule. It is slightly higher compared to the theoretical value, which is a 5.39 joule. The error between the experimental value and theoretical value is a 1.15%. The hardness profile shows the steel welding zone has a higher hardness value compared to the other region that cause a recrystallization in this region. The microstructure analysis show the aluminium alloy 6061 and aluminium alloy 6075 will produce 3 sub-layers at the welded zone. The microstructure analysis as a proof that the grain size becomes the finest to work to the welding zone. That's all. Thank you for the listening.